Right, so there's three ways you can disturb an equilibrium in Le Chatliers Principle. One of them is to change the concentrations, alter the concentrations of the reactants or products. Okay, so my first question to you guys is this an equilibrium? Okay, looking at the arrows and see how they go back and forth. This definitely is an equilibrium reaction. And so it's in an equilibrium, it's settled, and we're going to disturb this equilibrium. How will we disturb it? The first thing in part A we will do is remove O2. So what happens? Did you get one? So what happens if we remove O2? Which way will the reaction shift? Right or left? Okay, I heard shift left, and that's correct. So if you no, that's not correct. If you remove O2, where will it go? To the right. Okay, so if you remove O2, it will go to the side to make O2. So it shifts to the product side to the right. Okay, so anytime you think of Le Chatliers Principle, why is it so like this, blurry? It's not like the school is going to get us a new one. But if we remove O2, the reaction will shift to the side that replenishes the O2, and that's going to be shift right to the product side. What happens if we add KCl? So this time we're adding KCl. What happens when we add KCl? Which way will it go? Will it go to the side that has KCl, or will it go to the side to remove the KCl? Okay, left. Very good. It will shift to the reactant side. All right, KClO3 is added to the reaction mixture. Okay, so once again, we're adding and subtracting products, reactants. This time we're adding reactant. Which way will the reaction go? Towards the products or the reactants? Products, yes, you're right. Okay, it's going to shift to the product side. Okay, offset. Offset is the word that you want to think of for Le Chatliers Principle. Okay, O2 oxygen gas is added. So what happens if we add this? Shift left towards the reactant side. Okay, so this is one way that you can alter the equilibrium. And one of the ways we alter the equilibrium is by changing the concentrations, adding or removing reactants or products. Another way we can do it is by changing the pressure. Another way we can do it is by changing the concentration, the temperature. Okay. All right, so let's go to page 2 here. Okay, another way we can mess up an equilibrium is by changing the pressure. Okay, increasing or decreasing the pressure. So for this, we recognize that we're dealing with gases. Okay, gases. So anytime you see an equilibrium, and what else do you see? Gases, you can alter the pressure. So what happens if we increase the volume? Increasing the volume is the same thing as what? In terms of pressure, remember Boyle's law from Chem 1, Boyle's law. Increasing the volume is the same as doing what to the pressure? Here we go.
Thank you.
Yes, decreasing the pressure. Okay, so if you decrease the pressure, which way will the reaction shift? It will shift to the side that has more pressure. So which side has more pressure? 1 mole of I2 or 2 moles of I? 1 or 2, yes. Okay. Okay, so which side will this reaction shift? It will shift to the right. Okay, it will shift to the right because decreasing pressure, the offset is increasing pressure. Shift to the product side, shift right. Shift to the right. Okay, volume is decreased. All right, so increasing the volume means decreasing the pressure. Decreasing the volume means what? Okay, increasing the pressure. All right, so if you increase the pressure, which way will the reaction go? It will go to the side that has more pressure or less pressure. Okay, we'll go to the side with decreased pressure, and which side is that? Let's count here. How many moles? 2 plus 1 is 3. How many moles here? 2. I'm getting shift left. Okay, so that's what I think, and I think that's correct. It's going to shift left. All right, volume is decreased. If you decrease the volume, it's the same thing as, just as above, increasing the pressure. These are one and the same. Increasing the volume is the same thing as decreasing the pressure. This is from our Chem 1 topic known as Boyle's Law. So if you increase the pressure, what's the offset? It will go to the side that has decreased pressure. Okay, which side has decreased pressure? Okay, how many moles in the product side? 2. How many moles in the reactant side? Okay, so which way will it go? No effect on the equilibrium. It will shift neither, okay? Because you have 2 moles here, 2 moles there. Let me ask you this question with regards to Le Chatliers Principle. What other thing can you do to make sure it will have no effect? It will not change the equilibrium. What can you add? Yes, catalyst. Okay, you add a catalyst, it'll get the same effect. Okay, and remember, this is shifting neither to the product side, neither to the reactant side, because there's no change in the number of moles of gas. Our last thing here, there's a third thing that we can do, not decrease the pressure for gases, not decrease the concentration. Third thing we can do is we can increase or decrease the temperature. Okay. All right, so let's go through this one here. Okay, So is this in equilibrium? The answer is yes. And then it's asking us which disturbance will favor CH4 at equilibrium. We'll just answer which way the equilibrium will go, left or right. Okay, adding more C to the reaction mixture. Which way will this go? So this will actually favor CH4. CH4 is called methane. Methane. It's an alkane. Remember this? Alkanes, methanes. Adding more H2 to the reaction mixture. Which way will it go? Okay, it's going to shift to the right. That's going to favor CH4. Okay, raising the temperature of the reaction mixture. Raising the temperature of the reaction mixture. I forgot to highlight an important point here. And the fact is, what should I highlight? Yes, very good. This is an exothermic reaction. Right, so if it's an exothermic reaction, there's something that is also released, and that is heat. Okay, heat is also released in this exothermic reaction. So now we raise the temperature. Okay, raising the temperature. Okay, if we raise the temperature, which way will the reaction shift? Okay, it will shift to the left. Okay, so this one favors CH4. This one won't. Okay. Lowering the temperature. Lowering the temperature means removing heat. So if we remove heat, which way will the reaction go? It'll go to the side that has heat because we removed it. Remember the offset? So it's going to shift right. Okay, adding a catalyst to the reaction mixture. I think you answered this already, Sam. Where will this shift? Neither, no. Okay, adding neon gas. Where will this shift? Okay, do you see neon here? This is carbon, this is hydrogen, this is methane. It's not even part of the reaction. This is also neither. Okay. If I were to write the equilibrium constant for this in terms of pressure, what would it be? P stands for pressure of CH4 divided by the pressure of H2. What should I do with that pressure? Square it. Okay, do I add the carbon? No, because it's a solid. Okay, no solids. Okay, so I could also write the same expression in terms of concentrations. Alright, so these are the ways that we can change and alter an equilibrium. Okay, remember, when we're writing the equilibrium constant, we don't add solids and we don't add liquids. Alright, so this is the end of chapter 14. Let's go over some new material that will not be on the exam. So our exam is scheduled for after spring break. So it will be after spring break. It will cover chapter 13 and chapter 14, chapters 13 and 14. So this material, it will be on test 3, which is not going to be after spring break. I believe it's the week after spring break. It is the week after spring break, but I think it's a Wednesday or a Monday. anyways, I'll look at the syllabus and find out. We'll have a review Wednesday. Okay, so let's plan for a review Wednesday. So make sure you come to that class or watch the video for that class for Wednesday's lecture. All right, so chapter 15 is on acid-base chemistry. How many of you have heard of the term acids before? How about the term bases? Okay, so we'll go into a very deep dive into what an acid is and what a base is. There's different types of acids. The acids that I want to teach you are called Bronsted acids. Bronsted acids. There we go. Right? And, just as they are Bronsted acids, they are also Bronsted bases. Okay, usually acids have an H out in front. Okay? H. So Bronsted acids, what they do is they deliver protons. So what is a proton? Okay, a proton is H plus. That's one way I write a proton. There's another way. Okay, there's another way that we can write protons, and that is H3O plus. Okay, so the way I'm teaching it to you, these are one and the same. This is an important point. The way I'm teaching this to you, H plus, which is called a proton, okay, we're going to make it the same as H3O plus, which is technically called a hydromonium ion. Sorry. So once again, a very important point. Okay, just to make things simplified and make our life a little bit easier, H plus is the same thing as hydromonium ion. Okay, and H plus means a proton. Hydromonium ion is a proton, but when you see this or this, which I'm teaching you as one and the same, we want to think of the term acid. Okay, acid. Okay, so these are hallmarks of acid. If you see this anywhere in the equation, okay, that means it's an acid. Okay, acidity. So acids deliver these things called protons. They donate. Deliver, donate, however you want to put it. Protons. Okay, Bronsted bases. For every donor, there's who? There's someone who, if you give me a proton, I receive it. I receive it. For every donor, there is a receiver. So these Bronsted bases receive protons. I've also heard it being called that they abstract protons. Abstract? Okay, abstract protons. So those are Bronsted bases. Anytime you see a Bronsted base, it's a substance that has taken a proton. Okay, taken a proton. Okay. So another thing, I want you to associate bases with this. Okay, I want you to associate bases with OH minus. Anybody remember what this is called? Okay, this is called the hydroxide ion. Okay, so what do I want you to associate with base? Hydroxide ion. What do I want you to associate with acid? H plus, proton, or hydromonium ion. Okay, the way I'm teaching it to you, these are one and the same. All right, now back to my point here. So what does an acid do? It donates protons. Acids react with water. Okay, and acids, I'm just going to call HA, I'm going to call it an acid. I'm going to call it an acid. There's many acids. There's hundreds and hundreds of acids. Okay? Entire lists if you look at it on the internet or in the back of your textbook. So we're going to say any acid is going to react with water hydrochloric acid, nitric acid, sulfuric acid. Remember all these acids you learned in Chem 1? Okay, the acids are going to react with water, and what do acids do? They deliver H plus. If it's a strong acid, it's going to do it really, really, really strong, go 100% this way. But if it's a weak acid or doesn't have much, juice to it, then it would be an equilibrium. This donates the H plus, that's what acids do, and you're going to get H3O plus. All of this is dissolved in water, and you're going to get A minus, also dissolved in that water. Okay. Right. Like I said before, this H3O plus is the same thing as H plus. All right. So if it's a weak acid, it's going to go, 10%, 20%, 50%, 60%. Forget how fast it goes or how far it goes. The point being it's not 100%, so it's at equilibrium and giving us H3O plus and A minus. Right, so this has what we're going to call a Ka, equilibrium constant for the acid. It's products over reactants. Okay, no liquids. Right, so that would be Ka at some temperature. All right. So just a couple of words here. We're going to call HA the acid. We're going to call H2O the base. Why am I calling water the base? Because it took that proton, it received that proton from the acid. Okay, HA becomes A minus when it donates that proton. So we're going to call this the conjugate base, CB, conjugate base. And H2O picked up the proton, giving you H3O plus. We're going to call that the conjugate acid. So this is a couple. Conjugate acid, conjugate base couple. Right, don't forget the minus sign here. Don't forget the plus sign here. Okay, I'd like for you to know this equation. Okay. Okay, we're going to do the same thing. Okay, instead of Ka, we're going to do Kb. What do you think the A stands for here? The A stands for acid. Now we're going to do a Kb. I also want you to memorize this. Okay, so this conjugate base can also react with water if it's a weak conjugate base. If it's a strong base, all bets are off because this goes 100%, one arrow. So what do bases do? They receive protons. And who donates the protons? This is what makes water really, really fascinating to a lot of biologists and chemists. is that here water can donate the proton. And what will you get? Okay, you're going to get OH minus plus HA aqueous. Okay, I want you to memorize this as our general, very general form of KB. We will replace this with real chemicals in this chapter. So what is KB? It's products over reactants. Okay, why do we not put water in there? Just don't put water because it's a liquid. Okay, like before, here A minus is going to be our base. It abstracted the proton to give us HA, so these guys are a couple, conjugate acid. H2O is acting as a base here, so it becomes a base. It's acting as an acid here, I'm sorry. It's acting like an acid here because it donates the proton. When it donates the proton, it becomes OH minus. This is the conjugate base. Okay, so here we have a couple. Here we have a couple. Conjugate acid-base couple. This is called the acid. This is its conjugate base. This is the base. This is its conjugate acid. Okay, so I want you to know the Ka and Kb. Okay. This one would be the generic version for the acid. This one would be the generic version for the base. Okay. I'm going to do something now. Let's see if you remember what happens if we add these two reactions together. Okay, I'm going to add these two equilibrium reactions. One thing, if I add this one, we'll call it 1. I'll add it to this one, we'll call it 2. What cancels? Do you guys see what cancels when we add them together? This HA cancels out with this HA. Anything else that cancels? The A minus cancels, the reactants and products cancels. When you add two equilibrium reactions, you don't add these two, but you multiply. You remember this? Okay, you multiply. Okay, that was from one of the videos when we were during the snow days. When you add two equilibrium reactions, what do you do to the equilibrium constants? You don't add them. What do? You multiply them. So this cancels with this cancels with that. So you're going to get 2H2O is in an equilibrium with H3O plus OH minus. We're going to call this KW, which is nothing more than Ka times Kb. This is the second thing I want you to know. Ka times Kb is equal to Kw. So I want you guys to know this. I want you guys to know this. And then when we add those two reactions together, we get Kw. So Kw, if you look it up, is 1.00 times 10 to the minus 14. Okay, this is at 25 degrees C. This is Kw. So if you take any of these chemistry exams, okay, I think maybe the MCAT, they talk about this, I believe. So Kw is 1.00 times 10 to the minus 14. Okay, which is Ka times Kb. All right. what does Kw equal? Ka times Kb. It's also products over reactants. Okay. Products over reactants. But why do we not put water in the denominator? Because it's a liquid. Okay, so liquids don't go in there. And this is going to equal to 1 times 10 to the minus 14. And then Kw, as we mentioned before, is nothing more than Ka times Kb. So these things I'd like for you to know for this chapter. All right, let's take a look at this right here. Kw equals H3O plus times OH minus. Let's take a look at this. All right, I'm going to rewrite it, and let's do some manipulations here. Like I said, the constant for this, okay, at 25 degrees C is 1.00 times 10 to the minus 14. Okay, this is coming from this equilibrium, which we're calling Kw. Right, what I'm going to do now is I'm going to take the minus log of both sides of the equations, okay? So not just the log, but the minus log. Okay. So remember, acids are going to donate a proton. We're going to call it HA. Bases are going to take a proton. We're going to call that A minus. The conjugate base to this conjugate acid. We add the acid with its conjugate base, the Ka reaction for the acid, the Kb reaction for the base. Just so happens when we add them up together, we get the equilibrium constant for water. So water is in an equilibrium. 1 times 10 to the minus 14. Okay, I was reading a statistic. I don't remember where it was or what textbook it was. But 10 to the minus 14 is a very small number. So apparently 1 in I don't know how they figured it out, but 1 water molecule out of a trillion, 1 out of a trillion will go this way to give you 1 acid and 1 base. Acid in the form of H plus, H3O plus, base in the form of OH minus. 1 out of a trillion. Okay, so that's a very small equilibrium constant. Definitely favors the left-hand side, but 1 in every trillion will go this way and give you a source of acid and base. And interestingly enough, water in this reaction is acting like an acid, and water here is acting like a base. Water can do this, can be an acid and a base. Okay? A weak acid and a weak base. All right, let's go back to here. Okay, this Kw represents this equilibrium. We're just going to take the minus log of both sides of the equations. All right, so before we commence further, just want to tell you a little bit about some log rules. Okay, there's a log rule where log AB is equal to log of A plus log of B. Okay, so that is from trigonometry. Right? It's not something you need to know. Okay. And another thing you need to know is this lowercase p is called power. Okay, power. So the power of something. Okay, this power p is minus the log of something. Okay, so if power of, I'll just say x. Okay, this will be minus the log of x. Right, the p represents the power of whatever is in the parentheses. So p of, I don't know, VJ. Okay. minus the log of Vj. Okay. P of U, Sam, is minus the log. Okay, so whatever is in the parentheses, you do minus the log. Whatever's in the parentheses, you do minus the log. That implies power. Power means minus log. So P of x is minus the log of x. Okay, this is all trig and math. Okay, lowercase p is power. All right, with that being said, we're going to take the minus log of both sides. So minus the log of 1.00 times 10 to the minus 14 equals minus the log of H3O plus times OH minus. All right, what is minus the log of 1 times 10 to the minus 14 on our calculator? You can go ahead and do that. Minus the log of AB is nothing more than, okay, minus the log of 1 times 10 to the minus 14 is 14. Okay, log AB is log A, so we're going to do minus the log of H3O plus log B plus a minus the log of OH minus. Okay. So we have our first, or, well, actually several things I'd like for you to know. This, was it 1, 2, 3? The fourth thing I'd like for you to know is that 14 is equal to minus the log of H plus. But we're going to call minus the log of H plus pH. Okay, the power of the acid, pH. Plus minus the log of OH minus is the power of OH. We'll call that POH. Okay, this is the next thing I'd like for you guys to know. 14 is equal to pH plus POH. Okay. Have you heard of this term pH before? Okay, maybe in biology class or chemistry class. Okay, pH. Okay, it's the power of the acid in the substance. Okay, juice, orange juice has a pH of about 3. Your blood will have a pH of about 7.2, I think. Okay, if it goes higher or way high or way low, then that's a health issue. Okay, that's something that you have to worry about. It means your body's not working properly. All right, so pH is minus the log of the hydromonium ion concentration. I'm going to call it H plus, but I could also call it H3O plus. That is pH. Okay. If we want to go back, let's say you're given a pH in a problem, and you want to figure out the hydrogen ion concentration corresponding to that pH. Okay, you're going to do the anti-log. It's the same for POH. Okay, the power of the base in terms of OH minus is this. And if we want to go back, and figure out the hydroxide ion concentration corresponding to that POH, you'll do 10 to the power of minus POH. Okay, so, and then another equation is pH plus POH is equal to 14. Right, these numbers are scales. Okay. So there's something called a pH scale. Okay, there's something called a POH scale. Okay, these are all scales. Okay, which means that they have no units. This is a great thing for us because now K, equilibrium constant, capital K, equilibrium constant has no units. Okay, this pH, it being a scale, will have no units. Okay, so don't put units by pH or pOH. It's just a scale telling you the power of the acid in the substance or the power of the OH minus, the power of the base in this substance. All right, so this is the next thing I'd like for you to learn. All right. All right, let's take a look now here on these equations. So you should know this, know these equilibrium constants, what they mean. We'll put real acids and real bases later on. Definitely you should know this. Okay. And then most definitely you should know this and this. Okay. I think this is something all biology, chemistry majors probably have to memorize. All right, let's look at this one before we head off. Okay, Kw is equal to Ka times Kb. All right. Just as before, Kw for water at 25 degrees is 1.00 times 10 to the minus 14 equals Ka times Kb, the equilibrium constant for the acid, the equilibrium constant for its conjugate base. We will, like before, take the minus log of both sides. So minus the log of 1.00 times 10 to the minus 14 equals minus the log of Ka times Kb. Okay, remember what log AB is. Log AB is nothing more than log of A plus log of B. And minus the log of 1 times 10 to the minus 14 is what number? 14. Minus log of Ka plus minus log of Kb. Okay, we're going to call minus log of Ka pKa. Okay, pKa. Okay, this is a big deal in the biochemistry and pharmacology, drugs, all that stuff. And minus the log of Kb, we're going to call pKb, pKb. And then yet another thing that we must know. Okay. The power of the Ka is the power of that acid in giving you protons. pKb is the power, okay, the power of that base in taking that proton. Okay. Just like before. Okay, just like before, we have our pKa is equal to minus the log of Ka. Okay, pKb, the equilibrium constant for the base, is minus the log of Kb. If we want to go back and get the equilibrium constant for that acid, if we want to go back and get the equilibrium constant for that acid, okay, we will take 10 to the power of minus pKa. If we want to go back and back calculate the equilibrium constant for that base, equilibrium constant is products over reactants, no solids, no liquids. If we want to go back and get the equilibrium constant for that base, it's 10 to the power of minus Kb, the anti-log. Okay, the anti-log on your calculator. Okay, the anti-log, which is shift log. Okay, shift log, not log, okay, but shift log. not log, okay, but the anti-log, which is 10 to the power of minus the Ka or minus the pH, whatever. All right, like before, your pKa and Ka, well, the equilibrium constant we've learned from chapter 14 is unitless. There are no units in the equilibrium constant. And like the pH scale, pOH scale, the pKa and pKb are scales comparing which acid is a stronger acid than the other. Okay. So let's take a look at this for a second here. If we have a very large equilibrium constant for that acid, what does it favor, products or reactants? The number is very large. Okay. Let's say you have $1 million, okay, even though there's no units. But let's say there's $1 million. Are you moving forward or backward in your life? Okay, a very large Ka for that acid means that it's a very good acid. It's very good at this reaction. So a large pKa basically means it's a good acid, but if you look at the math, minus the log of pKa, this corresponds to a low value of pKa because of minus log, the math. So this represents a good acid. Okay, the strongest acid will have a large Ka, like hydrochloric acid, but a very, very low pKa. Okay, the strongest base will have a large Kb. Okay, it's a large value. If you have $1 million, you're moving towards the product side. But because of the minus log math, the pKb is going to be very low. Okay, a large Kb. This is a very good base in terms of taking away protons. Right, finally, if you have a large pH, okay, what does that mean? Are you a good acid or a good base? What did we say here? A good acid has a large Ka but low pKa. So a large pH would mean what? Okay, it would mean a low H plus concentration, which would mean it's not a good acid. Okay. What would be a strong acid in its stead? Okay, in its stead, something that has a low pH. What does that mean? High concentration of H plus. And if you know an acid gives off a large H plus, what does that make it? A strong acid or a weak acid? If an acid gives off a lot of H plus, then you know it's a strong acid. Okay. So that is our little intro into acid-base chemistry. By the way, the same thing occurs for the base also. Okay. If your pH is high, that means your pOH is low. Okay, because they have to equal to 14. Okay. All right, so I am overboard, and I will see you all on Wednesday, and some of you I'll see in the lab as well.